Hello, everybody. Welcome to another discussion dynamics. Please finish your conversations very slowly, okay? Because I would like to start. All right. Plan for today is following. Topic of today is relative motion. Plus, I will just remind you what kinematic constraints are, and today we will just see inextensible rope and ground and incline. Yeah, later this semester we will learn about some extra kinematic constraints you already seen in statics or physics 202. I hope that you did, actually, because I don't know what they teach you on statics. And I don't know if you learned, even if they teach you well. Yeah. So basically, kinematic constraints are things in the system that we just replace with forces. Yeah, we remove the kinematic constraint and we replace it with a force acting on the body. You know that. Yeah, for example, if we have a ground or incline, we replace it with so-called normal force. Yes. If there is an inextensible rope, we'll just replace it with a tension in the rope. Yeah, you will see today. We will not see it today. Yeah, but they also. Oh, wait a second. We will do that later this semester. Yeah. Today we'll just see how that impacts our motion, and we will do just two examples. Yeah, example number one, example number two. From quick reminders, these videos are being recorded, and I actually improved our channel. Let me show you. So if you now go to our channel where I post these discussions, and let's say that you go to our last discussion from Friday. Yeah. Me talking, yeah. Good to know. Yeah. So I included these chapters here, okay? So you don't have to watch the entire thing. If you are, for example, interested in only example number two, just click on example number two and you have example number two, okay? You knew it already, you know how to do it already. I just thought that it's nice to add it to our channel, so it will save your time. Okay, if you're interested, I know, in brief lecture review, yeah, here it is, yeah. Okay. So that's it from the news, actually. Yeah. Yes, IJ. I have stuff to do. Like, maybe after, maybe I think that this discussion will last like 40 minutes, so I will stay here for 10 minutes only for you, AJ. Okay? Yeah. Okay. Okay. And what else? Practice makes progress. Yeah. Don't forget that. Yeah. I know that it's very tempting to use solution manuals. Yeah, because it's like zero time you spend on your homework, but it's zero investment in your future. Yes. Yeah. So just try to solve homework by your own. Yeah. Example number one. Are there any questions? Did I forget about anything? And that was very bad timing, IJ, asking about that quiz. Like, of course, I'm not going to do it right now, yeah, but maybe after the discussion. Okay, please familiarize yourself with the problem statement before we start our solution. All right, I see that some of you are drawing, but I hope that you don't mind, guys, if I am going to start talking. Okay, so we have our pulley system. Yep, here. We know everything about velocity and acceleration of this point A. Yep, we know velocity A and velocity A and acceleration A. I even forgot to put numbers here. Yeah, so it should be 3 feet per second and 1 feet per second square. Okay, and they ask us to find VG and AG. Okay, of that block. All right, that's all. Yeah, and all the ropes are inextensible. So I would like to start solution. How many ropes do you see, guys? So this is how I solve those problems. If there's like many ropes in the picture, I just start with that question. How many ropes do we have in the system? Anybody? Means 3. 3, I accept also 4. We will see. That fourth one will come in the solution later, okay? So let me, yeah, there are 3, exactly 3. But if you say 4, I also agree. You will see why. So this is our first rope, red one, okay? Red rope is first rope. Then this is our second rope, yeah? Green one. And the third one will be blue, okay? So it has 4 chunks, yeah? This is first chunk of our rope. Second, third, and fourth. All right. So I would like to express their lengths, okay? Because their lengths are constant. I'm gonna add something here, guys. So red rope length of red rope is L1 and it's constant, okay? Green one has length 2, L2, and it's also constant. And blue one, surprisingly, has length L3, okay? Which is also surprisingly constant. Ropes are inextensible. Okay, let's model them, okay? Let's put it in some mathematical terms. But before we do it, let us maybe introduce some elevations, define some elevations in the drawing, okay? So I would like to get rid of this thing, this equivalent drawing, and I would like to introduce datum here. This is our datum, okay? No, not this. This is our datum. And I would like to define the elevation of this point B, as YB. Okay, this point analogically will have elevation YC. This guy has no other choice than having elevation YD. This is YA. And our block will have YG, okay? Yeah. Isabel? Ivan? And Liz, are you here? If you are, you didn't put your name on the list. It's fine. I just want to let you know. Okay, so we have those 5 elevations, okay? And we can use them to express the lengths of our ropes. So I will start maybe with rope number 1, okay? So we have L1, and I believe that this chunk of the rope has length YA minus YD plus the other chunk, yeah, this chunk. This will be YG minus YD. That's it. This is the length of our rope. This is how length of our rope changes in time, okay? How about green one? So I don't know, guys, do you want to help me or not? I don't know. It's like easy question. Okay, so very quickly, okay. This chunk, how long is this chunk? The small one. Okay, YD minus YC. And the other one, you know, I'm not going to even ask you, okay? The other one will be YG minus YC. yg minus yc, yeah. Let me just scroll a little bit. And now the blue one, I hear you guys that you know how to do it. So that one will be yg plus these three little chunks, yes, these three little blue chunks, 1, 2, and 3. So that would be 3yb. All right, that's it. I see your hand. Wait a second. Yes? What was the question?
We don't take into account the length of the rope that is in contact with the fluid?
No, no. Do you know why? Because it doesn't. I will also explain it at the end of it, yeah, at the end of the discussion. Okay. We don't. Okay, so that's it. Let me. Any other questions? Do you see? This is like basically mathematical modeling, yes, of the length of the rope. Yeah. So now let me just put it in order, okay? So I believe that L1 is equal to YA minus 2YD plus YG, okay? L2 is equal to YD minus 2YC plus YG, and L3 is equal to 3YB plus YG. And all of these lengths are constant, by the way. Okay, so we have our expressions for lengths, but we would like to get to the velocity and acceleration level, yeah? So in order to get to velocity level, you guys know what we should do. We should basically take first time derivative, yeah? Of these three equations. And thanks to the nowadays technology, I can copy paste it, yeah? So I would like to apologize to everybody who is using pen and paper. I hope you can forgive me. So first of all, the derivative of the left-hand side is 0, yeah, always 0, 0, 0. Why? Because L1, L2, and L3 are constant, yes? And I can basically, you can skip that part maybe, yeah? I can copy paste these expressions, and I can just put everywhere dot. I can put dot above each of the things, yeah? Dot, 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 yeah? Or I can replace y dot with v basically, yeah? I can do it here. I'm also going to copy paste, so I hope guys that you won't hate me or something, yeah? Sorry for that. Yeah, I'm just going to replace y dots with v everywhere. So we have VA to VD, VG. Okay. I will wait like 30 seconds, okay, or like 40 seconds. Yes.
Is there a reason why we're not looking at the rope?
I will get there. There's not any particular reason. Okay, so but we are gonna get there in 45 seconds. Okay. So let's see what do we know? We just know we have three. First of all, we have three equations. Yeah, three equations, and we have this thing that is known. Okay, only this thing is known. VA. They gave it to us. Yeah, and let's see how many unknowns do we have. We have VD that is unknown, VG, VC, and VB. Dang, we have four unknowns. Yeah. unsolvable. Yes, we have more unknowns than equations. We cannot solve such system. And Trevor had an idea how to find the fourth equation. Trevor. Exactly. So Trevor said that. Wait a second, Michael. We have actually we have 4 ropes in here. Yes, because there's also that little chunk in here. Yeah, the orange rope. L4 is constant as well. Okay, let's speak mathematics, Trevor. What do you think? So what this orange rope, what information it gives us? What useful information we know that can help us here?
Well, the length would be YC minus YB.
Exactly. So L4 is YC minus YB. And if you guys take first time derivative of that, you will end up with VC equal to VB. And this is exactly the fourth equation we're looking for. Thank you. Okay, so VC equals to VB. All right, so all of a sudden, we have 4 equations, yes? We have 4 equations, and this is solvable. Okay. So I am like 300% sure, guys, that you know how to solve that system. However, I'm going to do it quickly, okay? Just give me like 1 minute to solve it, okay? I will show you the steps, okay? So I numbered the equations. We have 1, 2, 3, 4, and I would like to plug equation number 4 to equation number 3, yeah? And that will give us VC that is equal to minus 1/3 of VG, okay? And let's call this equation star, okay? Now let's plug in star into 2, and we will have 0 is equal to VD plus 2/3 VG plus VG, okay? So that will tell us that VD is equal to minus 5/3 VG, okay? And let's call this one equation double star, okay? And now let's plug double star into 1. And we'll end up with, very quickly, 0 is equal to VA plus 10/3 VG plus VG, okay? And thanks to that, we know that VG, exactly what they are asking us for. Yeah, VG is equal to minus 3/13 VA. Great. We are solved basically part number A. So this is VG expressed as function of VA. Or just to save some ink, VG is a function of VA. Okay, before we plug in values, because if we plug in values, we solved part A. Can anybody just tell me how to quickly find AG? Once we know that, how to find AG? Yeah, exactly. So what's the answer? Minus 313 AA. Thank you. That's it. So that will be, yeah, did a deal of that. Okay, all right. Plug in values. And we have VG is equal to minus 313 times 3. Grab your calculators and obtain that this is equal to minus 0.6923 feet per second. Okay, when it comes to magnitude, we will talk about vector in a second. AG is minus 3 divided by 13 times 1, and this is approximately minus 0.2308 feet per second square. Okay, so we obtained this. These are our values. By the way, they are all negative. Yeah, they're all negative, and these dice were pointing downwards. Yes, VA and AA were pointing downwards. So VG and AG must point upwards. Yes, because of these negative values here. Okay, so you can also write it here that VG points up, or you can actually write it here maybe. Yeah, VG points up and AG points up. Okay, that's the first example of today. Any questions? Yes. Yeah, because of magnitude. Yeah, you're right. Yeah, maybe you're right. Because I didn't solve it in magnitudes. Yeah, the reason why you have negative value here is that I didn't solve it in magnitudes. You know. And actually, what is your name? John. Okay, so actually you're right. This is a little bit I confused here. Yeah, if I do something, I should do it right. Yeah, you're right. So I should probably write. This is my answer. Answer. So I should put. Let's put these things in here. Okay, and this is our answer. VG is equal to 0.6923, yeah, feet per second. Clearly pointed up. Yes, it's clearly points up. Yeah, that's a good observation. Thank you. You have eye for detail, I must say. And this one is 0.2308. Thank you. Okay. Yeah, this is the end of the problem. The previous one, I was lying. That's the end of the problem. No, thank you, John. Yeah, because it's like magnitude. Yeah, this we use for magnitude. Yeah, you're right. Yeah. Okay. Any other questions? Yes, sir. Okay, sir. So you would like me to erase that arrow? Yes. This arrow. I can erase it. It's fine. Yes. Yeah. Or this arrow. Or that arrow. Mm-hmm. Yeah. Okay, because you say that our coordinate system points this way. Yeah, maybe I'm just agreeing too much with you guys. Yeah, uh, you're right. Yeah, I agree with the second gentleman. Yeah, because this is our positive direction. Yes, it's like what we defined at the very beginning. Yes. Uh, I was lying for the second time. Okay, so whichever notation you choose. Okay, whichever notation you choose. You are right that according to our coordinate system we choose at the very beginning, these vectors point downwards and these point upwards. Okay. Yes. So no, John, no. I did it on purpose, just to check, just to see what's going on. Okay. No, I'm kidding. I was mistaken. Yeah. That gentleman is right. Yeah. Okay. And he's right because we define our coordinate system in a very quirky way. Okay, the positive direction points downwards. No. Okay. Please, no other questions. Are there any mistakes on the board? Any other mistakes on the board? Yeah. Okay. Question is number two. Let's do it. Let's do it. Please familiarize yourself with the problem statement before we start our solution. All right. So what do we have in here? We have two blocks. We have block A and block B. We know that block A has acceleration that is constant and it acts down the incline. We also know very important information that system starts from rest. Okay. And of course, our rope is inextensible. And that might be an interesting thing for you guys. So they ask us to find AB seen by this observer. So we have like an observer here on the incline, okay? It's a stationary observer. So this guy this is like first part of the problem, will be seen by this guy. But second part of the problem will be seen by guy sitting on A, on block A, okay? So this is the second part of the problem. So in the first part of the problem, they just ask us to find acceleration of block B. And in the second part of the problem, they ask us to find time needed for block B to move 0.2 meters relatively to this guy, to this observer that is attached to block A. Okay? Questions to the problem statement? So how many ropes do you have? Yes, one. Sorry for asking, by the way. Yeah, it's one rope here. Yeah. We can clearly see that this is one rope. Yeah. One. Okay. So let's say that that rope has length L, okay? And I believe that that rope consists of, let's put our datum here maybe, okay? This is our datum. And I think that we can define maybe this thing as XA and this thing as XB, okay? So we clearly have three blue chunks and one red chunk, yeah? So our rope has length XB plus 3XA. Okay, any questions?
Yeah. So why are you not measuring the small part of the rope on the one all the way down toward the ground? That's connected to it.
Okay.
We don't measure that little bit of rope.
Yeah, it does not change the answer. The short answer is that it does not change direction during the motion. The only things that change the motion are those blue things and that red thing. These are the only parts that change lengths. I will elaborate on that after the discussion. If you would like to stay, please stay here. Yeah. If you guys don't want to hear my longer answer, you can leave after the discussion. Okay. I just have stuff to do. Okay. I must finish. So we are at position level. So now let's differentiate once and twice. Okay, just to get to velocity and acceleration. So L is constant, by the way. So that will be 0. This is equal to VB plus 3VA. And this will be equal to 0, AB plus 3AA. Okay. And that means that our AB is equal to minus 3AA. So this is actually the answer. This is acceleration B expressed in terms of it's AB seen by the observer stationary. Okay, so this is AB seen by stationary observer. Okay, let's find the value of that. So AB is equal to minus 3AA, and that was equal to minus 3A0. Plug in values, and this is exactly 11.1 meters second square. Okay, AB is equal to 11.1 meters second square. This is the answer, part A. Negative. Yes, sorry. Yeah. So it's negative. If it's negative, it will be pointing this way. Yes, it will be pointing this way. It will be up the board. Yeah, up the incline. Up the incline. Okay, I just wanna actually, I have one question about logistics. Guys, so I don't know why, but I usually write in this part of the screen. And this is annoying for you, yes? Especially for people in the back, yes? So I would like to apologize for that. So from now on, I will try to write in the center, okay? Yeah. The reason why I was doing that is that I see that some people are just still writing, and some people are still writing this part, That's why I'm showing them the upper part of the screen and I'm just writing at the bottom. Yeah. But it's annoying for you, yeah, a little bit. Yeah. So I will try to do it in the center. Sorry, I hope you don't mind. Okay. Or we'll see in the future, okay? Okay, that's the end. Any questions to what happened in part A? So now part B, okay? Part B. Part B. What they ask us for? Aha, they ask us to find time in relative motion, yes? So we have the same situation. The same situation. But this time, seen from or by observer attached to block A. Okay, so I think that happened yesterday on the lecture, yes? So AB is equal to AA plus AB seen from A, yeah? This is yesterday lecture. And ABA is equal to basically AB minus AA, yep? And this is our A relative, okay? I promise I will keep that in mind. Okay, A rel. This is our A relative. So let us plug in values, okay? So I believe that was minus 3A0 minus A0, yes? So that will be minus 4A0, yep? So this is our A relative. Minus 4A0. Do you mind, guys, if we speak magnitudes right now? Because we just care about relative displacement, okay? So let's just take the magnitude. Let's take magnitude, okay, of that. Let's take magnitude. Okay, so A rel is equal to 4A0, okay? And by the way, it's constant. It's also constant. Because A0 is constant, yeah? So they ask us to find time, yeah? And our acceleration is constant. So do you remember the discussion on projectile motion? That when acceleration is constant, we don't have to integrate. We can just use ready to go expressions, yeah? And for me, what is really interesting, we can do it regardless of the coordinate system. So this might be the most important part of this discussion. So if A is constant, you can always write this thing regardless of the coordinate system. VREL, so V relative, is going to be equal to V relative initial plus A relative T. And displacement relative will be X relative, which is equal to X relative initial plus V relative initial times time plus 1/2 of A relative, T squared. Yeah, because our A relative was constant. So in other words, regardless of what coordinate system you're using, Cartesian, polar coordinate system, or normal tangential coordinate system, if acceleration is constant, you can always write down these expressions in that particular coordinate system, yes? Just remember that that coordinate system rotates also, yes? But it's, I don't know, I find it beautiful and a little bit abstract, yeah? Have I lost you guys or no? Cool. Because I was lost yesterday when I was looking at it. But I give it a little of time to think and I figured that out. All right, and they asked us about displacement, yes? So they told us that we should find something when displacement is 0.2. So maybe you guys can tell me what is this? What is V relative at the beginning? Why? Exactly. This is 0. System starts from rest. System starts from rest. This one we found, yeah, that was like 4A0, yeah? And this guy will be 0, because we can choose always coordinate system that is coincident with our initial displacement at the beginning. Okay, so we basically have 0.2, and this is equal to 1/2 times 4A0 T square. Let's say, I don't know, T final, yeah, T final. So T final will be 0.4 divided by 4A0 square root. Plug in values, 0.4, 4 times 3.7, if I remember correctly. Grab your calculators and obtain that this will be equal to approximately 0.1644 seconds. Okay. This is time needed for displacement 0.2 in relative motion. Okay, and we still have 10 minutes, guys. There's a question?
Oh, why would you get rid of the negative on 4A0?
Because I wanted to solve the problem in magnitudes. Because it doesn't, you know why? Because it doesn't matter if you look at the problem from A perspective or B perspective. Yeah. So actually, we solved that problem for this guy attached to B. For this guy. Yeah, that guy that was attached to B. Yeah. Yeah. So it will take exactly the same time for that relative displacement. I hope, and you're not Kevin. What's your Drew? Yes. I hope I answer your question. Yeah, yeah. Anybody else? Okay, so I would like to propose that, guys, because this is all I prepared, unless there are more questions. Yeah. So I would like to propose that because there was question of Vincent and there was question of your name, Kevin. Yeah, Vincent. They asked me to explain why we don't care about these things and this black thing as well. Yeah. So if you don't want to hear it, thank you for today. I don't feel like calling you here. Yeah. But if you would like to hang out for like 5 more minutes, feel free to stay here. Yeah.
So basically, that L1 that we use, it's not like specifically the length of the rope. It's just the length that you find.
We'll see. Okay. Okay, guys. So for those of you who stayed here, yeah, yeah, yeah. Okay, I would like to have your attention. Excuse me, guys. Excuse me. There is discussion is still on. If you don't want to attend here, you can. If you don't want to attend it, you can leave. Okay. I would like to have silence. Thank you. Sorry. Thank you, guys. Okay. So I'm gonna do it very quickly. Okay. And I think that my explanation, I had actually the same question 1 hour ago, exactly the same question, and I did exactly the same. This time I will try to do nicer drawing. Okay. So. Okay, very quickly, very quickly. So this is our situation at the beginning, okay? Let's say time 0 seconds, okay? So we have these guys aligned here, okay? And I believe that we have this thing in here a little bit larger, and this one a little bit larger. Oh, shoot. Just give me a second, guys. Sorry. I need a second, okay? I'm gonna make a nice drawing. Okay. And here. Okay, so Kevin, what is your favorite number? 5. Okay, so we're gonna go for 6. Yeah, I'm kidding. So this is what happens at time instant 6 seconds. Okay, so I just would like to put a marker here. Okay, so these guys are aligned. Okay, these guys are aligned here. Okay, and I'm not going to do anything with that marker at 6 seconds. Basically, this guy, that box will move a little bit downwards. This box will move a little bit downwards, okay? While this guy will move a little bit upwards, yes? It will. Yeah, so this is our situation at time instant 5 seconds, as Kevin wanted, yeah? 5 seconds. So, what did I do wrong in here? So this thing, that circle, will travel with our thing, yeah? That circle will travel with our thing. And that means that these ropes will get larger. These ones will get larger. Do you see? Oh. This will get larger, larger, larger. This is attached in here. And this rope will get shorter. Okay? So now, you guys can clearly see that the only thing that we actually care about are those chunks. This chunk, and this chunk. And this guy did not change at all. That's why we can ignore it, yeah? So these blue things are longer than they were before. Because before they had this length, this length, this length, and this length, okay? This distance is unchanged. Do you see, Kevin? That's why I ignored it. It doesn't contribute anything in our modeling process because it is always the same. Yeah, that's why I define that blue things as 3xa, if I remember correctly. Okay, so very and the same explanation with those guys, Vince. So you ask me about, hey, why don't we include these things in here? Yeah, these green things. I don't care. They don't change. Yeah, they are like they are. This is the motion we don't care about. This is part of the picture we don't care about. It's always constant. Do you see it? Okay. So I just wanted to say exactly the same about the red thing. Yeah. So I don't know, give me 30 seconds, okay, please. So before it was longer. Now our thing moved a little bit upwards. The red thing is shorter. Yeah. So our XB, I believe. Yeah. XB just got shorter. Yeah. And we just calculated from here. Yeah. We don't care about the thing that is wrapped around the pulley, the thing. Yeah. Okay, guys. I hope I shed some light. Yes. Thank you for today, and make sure you enjoy your afternoon.